encryption. Okay, Zlib is just a packer, right? They just pack all the stuff. It's plain text ASCII what they send. What's interesting about it is that the bots or zombies, they poll the information. So they're asking the server, do you have any news for me? If so, please send them. Then the server sends back. But the server is not giving the commands. It's actually the client asking for commands. Old versions had like around 12 commands. Newer versions have 14. I'm not sure if we got the latest, but our last sample is from like somewhere September, October. Maybe there are newer commands. I have to admit, we have worked on. Oh, yes.
If they used proper public key challenge response, you couldn't be the command server, right?
Okay, the question is if they had used proper encryption, like public key encryption, authentication, right? The whole thing would not be possible. Well, what we could do is we could still connect because we know all the client stuff, right? We could authenticate to the server. But what we wanted to do is we want to implement the server, and that would not have been possible then, because we would have needed the keys on the server. This is for all the hackers out there that then see a machine and maybe hijack that machine, get down the keys from the commanding server and whatever. But the problem here is also that the commanding servers are also peers. They are not the ones that are controlled by the owners of the botnet. So it wouldn't be any use to have the keys inside one of those command servers because they could be hijacked as well, because they are just peers like all the others, right? But still the commands could have been signed, and that would have made it very much harder for us. Okay, here's how the protocol looks like after Zlib encryption, okay? First the client sends some hello message saying, okay, hello, my name is my computer. This is the actual computer name. I'm running Windows XP Service Pack 2, and my ID is this up there. And then the server answers, okay, your external host name is this, and this is your IP address. So always nice to know if you're netted or whatever to get your outside IP address. Okay, this has been known before, this handshake and the Zlib encryption, because you can black box that. Then there's a second command, which also has a number 2. There's number 2, the same ID and some other stuff, which is not so important here. And what all the guys that have black boxed have always seen is a 1 and colon? No, what's? Exclamation mark. Thank you. So a 1 and an exclamation mark. That's all that they've ever seen. So they thought, okay, it's probably part of the hello, like a second stage or whatever. We will come to that point on the next slide. Okay, the next step is to request the DDoS targets. So right now that we are the command server, we could DDoS anybody who we don't like. And the best is we can send spam, right? Right. We haven't done that yet because I don't know any good text, and I'm not a good writer. So if you have a good text, please come to me and we can have a look if we... What? All right, Mrs. Christmas, maybe the original executable, right? Okay, so this number 2 was somehow suspicious to us. It had no use at all, and nobody knew what it was for. So we had a closer look into the assembly source code, and there was some strange update thing, right? The string update is found at multiple places there, but here it was somehow suspicious, and at that point we could also identify the functions for all commands that are sent out, right? So we were pretty far ahead during that phase. And by injecting fake responses into memory, we didn't even have to wait for fake real command servers. We could just go to that point in the code and check what's happening there. And so we just altered the control flow to get to this point only. And if you have a look at this point, it's already pretty obvious what's happening. Okay, pretty obvious if you know how to adjust all the blocks, because I didn't have time to adjust them, sorry. So the first thing that is done is here on the right, from your point of view on the right, there's a string copy happening to update. Okay, sounds very interesting. If this is really update, and there are some other conditions that are true, there's an HTTP download command that is executed. And with this binary, there's a create process call afterwards. And this sounded very, very interesting to us. So we tried that, and we were pretty successful, right? So after knowing the search hash and telling everybody we know the results to the search as you are doing, then in the results saying, okay, this is the server you need to connect to. And then when they connect, we just send the update. And this update is really run on the machine. So we could inject like any executable we wanted to into the system. And now the point is, once you're on the machine, you want to remove the old storm worm. Because they may upload binaries too. And so then it's a war. Which binary is the strongest and is harder to disinfect and stuff. So the first thing we do is when entering a machine is to disinfect it, right? Remove the old storm worm. And, oh, there's a question? Right.
You mentioned there was randomness in the search hash generation.
Right.
Is that like a primitive form of load balancing? Although not all the hosts were there when the botnet was a lot bigger.
Right, okay, the question was, why are those hashes really random? Well, there are 32 different hashes the bots are searching for. And if this is some kind of load balancing, that's the question. Actually, it's putting less load on the overall DHT, but it would also be possible, I think, even with just one hash. But right, everybody's asking the same nodes then. Okay, maybe we can take this discussion afterwards, right? Because Georg disagrees, and we have to fight this out internally before we get the boxing equipment, and while Till is telling you how to disinfect from Storm. Thank you.
Yeah, okay, is it working? Okay, here comes the final part. So now we know how to gain control over a Storm peer. And as Felix already said, now the question is, what can we possibly send to a Storm peer and execute there? And the goal is, of course, to terminate running instances. So there might be even several instances running of different versions of Storm on one machine. The one thing we observed is that if you download Storm, a Storm sample from one of the web pages, for instance, the Dancing Skeleton page, if you download the Storm sample from there, you get samples with different checksums. So it's some sort of polymorphism is implemented there. I think it's not that you get a unique sample each time you download it, but yeah, it's at least we have several thousands of different samples. So what we cannot do is we cannot unpack it and do stuff with it. So our strategy is we must enumerate all processes running on a system and check whether they are Storm or not to identify the processes which we want to terminate. And our strategy is that we scan the memory of each process and by calling read process memory and then perform a simple pattern matching. And then we have to be careful because some versions of Storm inject threads into services exe or Explorer exe. And in these cases, we cannot simply terminate the process because if you terminate services exe, you terminate Windows, and this is not what we want. So in that case, we have to we have to identify the image on disk. We have to mark it so that it gets deleted upon the next reboot. And then we have to, no, this is the other case. Yeah. Anyway, we have to, if we can identify an image on disk, we have to delete it upon the next reboot. But in the case of a standalone process, we can simply terminate it. And if it's an injected thread, we need to terminate the thread. And this is done by injecting some kind of shellcode into the code segment of the thread. I guess I have a different slide. Yeah. The distinct pattern, the unique pattern, which can be used to identify a storm thread or a storm process, is the XOR key. It is 40 bytes long, so we have a very low false positive rate, as shown in the formula at the bottom of the slide. And we assume that it's safe to simply scan for this pattern in the process memory, and if we find it, we can safely assume that it's storm. This is the histogram of the XOR key. Georg, you made it, and I guess you wanted to show that it's results in the few false positives. Yeah. Anyway, here's an example memory map. We see services actually with different threads. Some have a PE header, some data sections, code sections, and at the bottom there's a standalone process. And we can now run through all memory sections and search for the XOR key by, we implemented the Boyer-Moore string matching algorithm because it's known to be one of the faster ones. And so we can now identify the threads and processes which are storm. And here is a shellcode we inject into a thread because, as I said before, a process can simply be terminated. And if you can guess which tool made this pretty graph, Marcus, you don't count, then you might be a candidate for one of the beers. What? I mean, which tool created the dot file? No, which tool created the dot file? Yeah, right. Okay, you get the beer. Okay, we reused existing shellcode here, which does some PEB location thing for the exit thread AP call, and then finally calls it so that the current thread terminates itself. What we do is we spread an obflat over the whole code section of the identified thread and place this little piece of shellcode at the very end of the code section. Okay, here are the final slides. I want to say a few words about how you can actually take over the Storm botnet. What you can do with our approach is you can take over the network from a single machine. But if you would do that, you would probably get an implicit DDoS because you receive so many connecting, overnet messages that you basically cannot handle it. So you DDoS yourself in an implicit manner. But you would probably also get explicitly DDoS because there are most likely some people which are pissed off and would DDoS you. But if you want to make that experience yourself, you can use the code we will be publishing maybe tonight or tomorrow once we figured out how to, attach it to an email. Okay, and the next step is what we thought about. How can you prevent from being DDoS? Prevent the DDoS attacks. You can take over Storm in a distributed manner. We already have a peer-to-peer network by hand. So you could recursively disinfect it. We could start with one node, which is marked red here, and this node can then inject this, the modified, the manipulated hashes itself, and automatically take over different further nodes. So the next step would be it would take over these nodes, and these would take over other nodes. So you will recursively take over the Storm network, and this is smart, this is fast, and it's not ready yet. So actually, you have to blame Felix because he didn't finish the reverse engineering part, which is Yeah, important for that part. Okay, now we come to the interesting part of this